NEC Section 250.142b addresses the protection of the equipment grounding conductor. This section of the National Electrical Code states that the equipment grounding conductor shall not be connected to a grounded neutral conductor or to an equipment conductor within the enclosure or cabinet for appliances, luminaires, or other utilization equipment connected by cord and plug. The key issue in this scenario involves a situation where an electrician connected both the neutral lead and the ground lead from new dimmers to the ground wire coming into a switch junction box. This action effectively turns the ground wire into a grounded neutral, which directly violates Section 250.142b of the NEC. The primary reason for this code requirement is that the equipment grounding conductor is designed to provide a low resistance path for fault current to flow back to the source. When it is connected to a grounded neutral, it creates a parallel path for fault current. This parallel path reduces the effectiveness of the grounding system, and this can potentially increase the risk of electrical shock or fire hazards. To correct this violation, the neutral lead from the new dimmers must be connected to the neutral wire coming into the switch junction box. The ground lead from the dimmer should be connected to the existing equipment grounding wire. This separation ensures that the grounding system functions as intended, providing a safe path for fault currents without compromising the neutral circuit. The NEC 250.142b is crucial for maintaining the integrity of the grounding system. The equipment grounding conductor ensures a low impedance path for fault currents, facilitating the quick operation of overcurrent protective devices like circuit breakers or fuses. If the grounding conductor is compromised or improperly connected, it can lead to several hazardous conditions. Firstly, a compromised grounding conductor can prevent the rapid clearing of faults, which means that a fault current may persist longer than intended. This can cause overheating of electrical components and increase the risk of fire. Secondly, it can increase the potential for electrical shock because the equipment grounding conductor is intended to keep the exposed metal parts of equipment at or near ground potential. If the grounding conductor is not functioning correctly, these parts can become energized during a fault, posing a shock hazard to anyone who comes into contact with them. Thirdly, the equipment grounding conductor helps to reduce electrical noise and interference. This is particularly important for sensitive electronic equipment, such as audio-video systems, computers, and medical devices. An improperly connected grounding conductor can allow noise to propagate through the system, which can disrupt the operation of this equipment. The NEC also addresses specific scenarios and exceptions related to grounding and neutral connections. It is important to understand these nuances to ensure compliance with the code. For example, the NEC provides specific rules for grounding separately derived systems such as generators and transformers. These rules ensure that the grounding system for these systems is properly coordinated with the main grounding system of the building. Another important aspect of grounding is the use of appropriate grounding electrodes. The NEC specifies the types of grounding electrodes that are permitted and the requirements for their installation. Common grounding electrodes include ground rods, metal water pipes, and concrete encased electrodes. The selection of the appropriate grounding electrode depends on the specific conditions at the site, such as soil resistivity and the availability of suitable electrodes. In addition to the NEC, there are other standards and best practices that can help to ensure electrical safety. One important standard is NFPA 70E, which is the standard for electrical safety in the workplace. This standard provides guidance on how to protect workers from electrical hazards, including shock, arc flash, and arc blast. NFPA 70E covers a wide range of topics, including hazard assessment, personal protective equipment, and safe work practices. It is essential for employers to comply with NFPA 70E to provide a safe working environment for their employees. To ensure compliance with the NEC and other relevant standards, it is important to have a thorough understanding of electrical principles and practices. This includes understanding the differences between grounding and bonding, the proper methods for installing grounding conductors, and the requirements for testing and inspecting grounding systems. It is also important to stay up to date with the latest changes to the NEC and other standards, as these changes can have a significant impact on electrical installations. Proper training and education are essential for electricians and other electrical workers. This training should cover not only the technical aspects of electrical work but also the safety procedures and best practices that are necessary to prevent accidents and injuries. Continuing education is also important to keep up with the latest technologies and techniques. When working with electrical systems, it is important to follow all safety precautions. This includes wearing appropriate personal protective equipment such as gloves, safety glasses, and arc-rated clothing. It is also important to energize equipment before working on it whenever possible. If it is not possible to energize the equipment, then it is important to use appropriate lockout-tagout procedures to prevent accidental energization. Electrical safety is a shared responsibility. Everyone who works with or around electrical systems has a role to play in preventing accidents and injuries. By following the NEC, NFPA 70E, and other relevant standards, and by adhering to safe work practices, it is possible to create a safe and reliable electrical system. The NEC provides detailed requirements for the sizing of equipment grounding conductors. These requirements are based on the size of the overcurrent protective device protecting the circuit. The larger the overcurrent protective device, the larger the equipment grounding conductor must be. This is because the equipment grounding conductor must be able to safely carry the fault current until the overcurrent protective device operates to clear the fault. The NEC also provides requirements for the installation of equipment grounding conductors. These conductors must be installed in a manner that protects them from physical damage and corrosion. They must also be securely fastened to the equipment they are grounding. In addition to equipment grounding conductors, the NEC also requires the use of bonding conductors. Bonding conductors are used to connect different metal parts of the electrical system together to ensure that they are all at the same potential. This helps to reduce the risk of electrical shock. The NEC provides specific requirements for the sizing and installation of bonding conductors. These requirements are based on the size of the circuit conductors and the type of metal being bonded. Grounding electrodes play a critical role in providing a low impedance path to earth for fault currents. The NEC specifies the types of grounding electrodes that are permitted, including ground rods, metal water pipes, and concrete encased electrodes. The selection of the appropriate grounding electrode depends on the specific conditions at the site. Ground rods are commonly used as grounding electrodes. They must be at least 8 feet long and must be driven into the ground until at least 8 feet of the rod is in contact with the soil. Metal water pipes can also be used as grounding electrodes. However, they must be in direct contact with the earth for at least 10 feet. Concrete encased electrodes, also known as UFA-grounds, are installed in the concrete foundation of a building. They provide a very effective grounding electrode due to the large surface area in contact with the earth. The NEC requires that grounding electrodes be tested to ensure that they provide a low impedance path to earth. This testing is typically done using a ground resistance tester. The ground resistance should be as low as possible, but it must not exceed 25 ohms. If the ground resistance is too high, then additional grounding electrodes must be installed to reduce the resistance. Regular inspection and maintenance of grounding systems are essential to ensure that they continue to function properly. Grounding connections should be checked for corrosion and tightness. Grounding conductors should be inspected for damage. Grounding electrodes should be tested periodically to ensure that they still provide a low impedance path to earth. Any problems that are found during inspection or testing should be corrected promptly. The NEC is a complex and comprehensive document. It is essential for electricians and other electrical workers to have a thorough understanding of the code in order to ensure that electrical systems are installed and maintained safely. Continuing education is important to keep up with the latest changes to the NEC. There are many resources available to help electricians and other electrical workers learn about the NEC. These resources include books, articles, websites, and training courses. By taking advantage of these resources, it is possible to stay up to date with the latest changes to the NEC and to ensure that electrical systems are installed and maintained safely. In the situation described, the electrician's actions of connecting both the neutral and ground leads from the new dimmers to the ground wire in the switch junction box not only violated NEC 250.142b but also created a potentially dangerous situation. By doing so, the electrician effectively turned the equipment grounding conductor into a current carrying conductor under normal operating conditions. This is problematic for several reasons. Firstly, the equipment grounding conductor is not designed to carry continuous current. It is intended to provide a low impedance path for fault current only. When it is forced to carry continuous current, it can overheat and potentially cause a fire. Secondly, the equipment grounding conductor is typically sized smaller than the neutral conductor. This means that it may not be able to safely carry the amount of current that is flowing through it. This can also lead to overheating and fire. Thirdly, the equipment grounding conductor is connected to the metal parts of equipment. This means that if the grounding conductor becomes energized, then the metal parts of the equipment will also become energized. This can create a shock hazard for anyone who comes into contact with the equipment. In addition to the safety hazards, this wiring configuration can also cause problems with the operation of the electrical system. For example, it can cause voltage fluctuations and interference with sensitive electronic equipment. It can also cause the ground fault circuit interrupters to trip unnecessarily. To correct this situation, it is essential to disconnect the neutral lead from the ground wire and connect it to the neutral conductor in the switch junction box. The ground lead from the dimmer should be connected to the equipment grounding conductor. This will ensure that the grounding system is functioning properly and that the equipment is protected from electrical shock. It is also important to check the wiring of all other similar circuits to ensure that they are wired correctly. If any other circuits are found to be wired incorrectly, then they should be corrected immediately. Electrical safety is paramount, and any wiring errors should be corrected promptly to prevent potential hazards. The NEC provides a comprehensive set of rules for electrical installations, and it is essential for electricians to follow these rules to ensure the safety of people and property. It is also important to stay up to date with the latest changes to the NEC, as these changes can have a significant impact on electrical installations. When in doubt, it is always best to consult with a qualified electrical inspector or engineer to ensure that the electrical system is installed and maintained safely. Remember that electrical work can be dangerous, and it should only be performed by qualified individuals who have the necessary training and experience. The information provided here is for educational purposes only and should not be considered a substitute for professional advice. Always consult with a qualified electrician or electrical engineer before performing any electrical work.